right, everybody. Hope you're doing well. Sorry about the banner. Hang on, let me get rid of that. There we go. Yeah, hope you're doing well. And give me just a little comment, a little chat if you are there, if you can hear me. I'd love to hear from you. And just know that we can go ahead and get started. But yeah, what I always ask people at the beginning of the stream, you know what? I'll even put up the slide that I use. Let's see here. Let's see if I can find that slide. I'm going to make it a little bigger than I did last time because last time it was kind of small. Yep, there it is. So I just introduced myself. So my name is Steven. And I'd love to hear from you if you could tell me your name or some greeting and which country you're logging on from, if you feel comfortable sharing. And I always also ask, what do you want to learn today? How can I help you learn what you're interested in? So those are all really important. And yeah, maybe I'll just ask, I'll answer those myself. So I'm logging on from the United States, from California. And yeah, I'm just hoping to learn from all of you. Hopefully you can get some good questions and some good feedback on the projects for today. So with that in mind, I'm going to give a few moments for folks to send a message about this. And I'm also going to send a registration link in the chat. Okay, because this is really important to be registered for the event. And I sent that link over, so you can check on it. It's important to get points for your team, and it's also important for just letting us know what you're interested in, the kind of content that you're curious about. Okay, so next we're going to go into the workshop itself. So let me pull up where we left off before. We had done a lot of different things, and I'll go ahead and present that. All right, so hopefully you can see now. And I'll present this and I'll talk through it a little bit to give you an idea of what we accomplished last time. So we used the Wikitext 2 dataset from Hugging Face. And that was a huge dataset of millions of text, millions of words from featured articles on Wikipedia. And then data cleaning, we did that too. We defined a simple cleaning function to remove, which the purpose was to remove HTML tags and extra white space. And then we used a pre-trained BERT tokenizer to tokenize sample text and the full data set. And we prepared for training. So we discussed padding and attention masks and using a data collator to automate those tasks. So those are just a few of the things we covered in the last part. I see 404 is there. So hi 404, good to see you. I'm glad because wanted to just make sure that things are running okay AV wise. So yeah, but we were here for this, so probably remember a lot of this stuff. That's what we were working on last time. But I have a few challenges for you. These are just things to think about relative to what we covered in the last workshop. So why don't you try tokenizing a different text sample? So there are many open source, publicly available data sets, just like the Wikipedia one we looked at, that you could check out and try to tokenize. And another thing you could try to do is adjust the max length parameter. So we saw that, that data collator, it padded the sentences up to some max length. And you could try to increase that, which would be similar to increasing the context window, or it would be necessary, I should say, for increasing the context window. So that's a really important thing too. You might see that the token IDs, the token IDs should change if you do either of these two things. All right, so here's another challenge. And I was just going to say, you remember we wrote a clean text function, which relied on regex to remove numbers and other unwanted characters. We could continue to do more regex expressions and further narrow that down. So yeah, just something to think about. Okay, but now we're going to move on to building an actual transformer model. So we'll build a minimal transformer model that will allow us to define some of these core components in the code. All right, and so first, self-attention is one of the concepts that we talked about before in the first part, but just to give you a reminder, it allows every token to attend to every other token in the sequence. And in our implementation, we split the representation into multiple heads for richer representation. So we showed how to do that in the last part. And then the feed-forward network, after the attention layer, each of those tokens' representations is processed by a small feed-forward network and applied independently at each position. So that is how we process the attention scores into some kind of output. And that's really important to understand. And actually, I realized that I should be sending you all the slides because that's kind of important. So I'm going to send them in the chat. People often ask for those slides. And I'll also send a copy of the notebook that we're working with today, which I did not send that one either. But yeah, this notebook is really useful and sort of tells you about what's happening. As I'm typing, it should update, so you can kind of get a live idea of what's going on. All right. So yeah, that's sort of where we're at right now. And yeah, let's continue to go along. So the next slide is putting it together and building a transformer block. So remember, a transformer block will typically consist of the following. So it'll consist of a multi-head self-attention. It will also consist of residual connection layer and layer normalization. And so that's where we're using those linear layers. And so then finally, the feed-forward network, where we put these things together. And so we're going to now integrate embeddings and positional encoding together into one. All right, so this is the next step here. So we will put the input tokens into dense vector representations using the token embeddings. So remember, embeddings is where we convert the token into a vector that has semantic meaning. Okay, so it's actually has some relationship to the other words in the vocabulary. And positional encoding is where, because with a transformer, we're processing tokens in parallel. So with the transformer, we would want to add a positional information, some sort of positional encoding, as it's called, so that the model knows the order in which these tokens are supposed to be understood. And for simplicity, we're going to use learnable positional embeddings. So that means that the model can actually learn the positional embeddings too. So we're going to try that out. And I have this interactive example where we're actually going to try and code this up. So let's go into our workshop. Here's our workshop, I believe. Oh, sorry, that's the wrong one. Here's our workshop. Last time we looked at a lot of really neat things, but I want to start us off with looking at that pseudocode that we wrote. I guess it's not a pseudocode because it really does work, but the idea is that we have some custom inputs. This is just we're making up some random input, but we might have some torch tensor. Torch.tensor. And let's just say we have some random vector here. And we'll say that this is just our example, right? And then we have some custom logits which we would apply some model to this custom input. And this is just a pseudocode, remember. So it won't actually be relevant or necessarily run in this case, but this is what we mean when we're talking about having this possibility here to have the token embeddings and the positional encoding. Okay, so the next thing we're going to talk about is training your model. And so for a language model, the typical training objective is to predict that next token in the sequence. So again, we're always wondering, given some of this context, what is the next word that we can expect to come out of this, this person's mouth? And so we're going to prepare two types of inputs. And so, we have something called Wikitext, for example, right? Where we're just looking at these Wikipedia articles. Well, what's the training data there? And the training data and the target data is actually coming from the same source. So those words are the input, just as they are in the text. But you'll hold off on the last word in each sequence, okay? In each sentence, in other words. And what you'll do with that last word is you will omit it from the input because we're going to shift all of the words over. Shift all the words over by one. And we'll essentially make it so that the targets are then the input sequence themselves, but just shifted over by one token. And we're even going to have an interactive example here where we try to create our own toy data set. And so I'm gonna show that to you. So first, I want to show you the transformer block itself, though. So that's going to be the first thing I'll show, and then we'll go to the next step. All right. So we're going to need a transformer block for this this training, and so let's go ahead and create that. The first thing we'll do is type class transformer block, and it will accept some neural network module. And there will be a few different things we're going to add into here. So this is really similar to what we've been doing so far. We'll define some constructor here. Okay. And so it'll have all the properties of a transformer block. And even more, so it'll also have an attention attribute, which remember we had that self-attention method from before. So which requires the model dimension and the number of heads. And you'll see it up here. I think it was quite far up actually at this point. It's been a long time since we did this. Yeah, here it is. So this is our self-attention. It takes Q, K, and V vectors. And this is the multi-head attention here. All right. So then the next thing that will be there is norm 1, which is a layer normalization. And what layer normalization does is it just makes the scales of the different features in the machine learning model that you're trying to optimize. It makes that scale all comparable. It makes all of those data sets comparable. And then the next thing we'll do is have our feed-forward network. So we'll do self.ff equals the layer normalization, or sorry, not the layer normalization, the feed-forward method. And this is not an NN method, it's just, we already defined that above actually. Let's see if we can find that. I know it's here somewhere. There it is. Feed forward, sorry. I lost it just as I was getting it. Okay, feed forward. Here it is. Here's the feed forward class. So we'll use this as well. And we'll just use that inside of this data set. And we have self.norm2. So once we pass the feed forward, once we pass through the feed forward, we'll do a second normalization because everything's gotten unnormalized by using our feed forward algorithm. And we'll just normalize it back to the dimension of the model, which is also known as the embedding dimension. And then finally, I want to add a dropout layer. Okay. So that'll be based on the dropout rate here. You might be asking, what is a dropout layer? We can ask that. What is a dropout layer? Let's see if it works. Okay. So this is a very good explanation right down here that you have a fraction of the neurons that are being quote unquote dropped out in order to see if that neural network is really depending on just one or two things in order to get the algorithm right. So you want to use this to prevent overfitting of your data. Okay. And then we'll continue. And we'll have some forward model. And remember, the forward model is very much based on attention with some residual connection, and then feed forward with some residual connection. So you might remember we talked about residual connection. And so if you look at what's happening here, you're taking the X and you're adding the dropped out attentions, and that is adding the residuals. And then you renormalize and set the X back to that, right? So it's going to sort of help us make sure that we don't overfit to any one solution. So if we go into our code itself, and we want to say that it will be self.norm1x plus the dropout layer. And then the feed forward will go recursively, And we'll do another self.norm with that exact same thing, except this time it is using dropout based on the feed forward output, which is really like used to be our final output in the first part of this workshop series. But now we're going to get a little bit fancier here. And yeah, so why don't we test the transformer block? And the way we'll do that is by just making some variable. Sorry, I should run this first and make sure. Yeah, see, there's a syntax error. Going to happen all the time to you. And I guess I didn't import NN. Let's see, it must be imported up here somewhere. I mean, obviously, this is sort of a messy way to write these things, right? But there it is. That's what we have to do in the Jupyter Notebook world. That's the fate that we're having to deal with. But yeah, let's see what happens with this. Okay, so it seemed to work, although I'm getting this error that self-attention is not defined. So we might have to try and get some definition for self-attention. I know there's a function up here, but yeah, let's just keep going for now, and maybe Gemini can help us figure out how to troubleshoot that. But for now, I guess we'll just keep going along. For our transformer block, I'm just going to check in on it actually, make sure I don't have the wrong thing. Okay, so I think I don't have the self-attention block here, but I can get that. So let me copy and paste those in. All right, so I put those on. And so I just pasted them so that we made sure that it all existed and was all consistent with our demo. All right, so let's try to run this. And we get no compilation error. And so we'll see if there's some kind of runtime error when we actually run this. But I'm pretty confident about it. And yeah, so that's how we do that. And now that we have a transformer block, we can actually create the transformer model. So we'll use a new class definition. And we'll have it input some module. And in this case, we're going to use those transformer blocks. And we're going to apply some of the skills and aspects of learning that we know from the transformer model as a whole. Right? And so let's try that actually. Let's try to do that. Well, let's see. Scroll down, give ourselves a little bit of space here. First, let's do a dunder method, just like we usually do. And I'm going to put everything that we would possibly need for our model in here. So we're going to definitely need some vocabulary size to tell the model our vocabulary, because that's going to determine the size of a lot of our matrices, right? A lot of our matrices. And then dmodel, which is that embedding dimension. Num heads, which is the number of multi-head attention heads that we'll need for this algorithm. And so remember that the number of heads has to go in evenly to the embedding dimension. So it can't be like 3 and 5. Those cannot be the heads and the embedding dimension. It has to be like 3 and 6. Right? So that the embedding dimension is twice the number of heads, for example. And then we have a few more parameters here. We have the max sequence length and the dropout. And it's trying to get me to do some super, which I will happily do, to just inherit a lot of the properties from itself. And then we're going to add an embedding layer first. So remember, embedding layer is a key aspect of transformer model. And we're going to use the NN module to access a pre-made embedding method. And we will use vocab size and demodel in order to embed into the demodel the semantic meaning of each word in the vocabulary. And then we have positional encoding. Okay, so we're going to also define something for positional encoding. Although this is a little bit wrong, I want to actually use a parameter module object, but we're going to use the following. We're going to say, excuse me here, torch dot zeros, and we'll say 1, comma max sequence length, comma, and then this should be demodel, right? So there's the positional encoding, or actually I'm going to call this positional embedding, because we're just embedding the positions as well as all the other information that's available from these data. And finally, we're going to have, oh, actually not finally yet, because we still have yet to make our actual layers, which are going to be the real secret sauce in this transformer model. But we'll start with nn.parameter, and we'll use the following, or I'm sorry, nn module list, because that lets us put multiple modules at once. So let's just use that, and we're going to use parenthesis and this actually is what I'm supposed to do. But yeah, so we're going to use the transformer block that we just wrote. So we just wrote a transformer block code, right? And we're going to pass in the arguments that we need, which included demodel, num heads. I don't like these suggestions, honestly. I'm going to do it myself. D_FF and dropout. And we're just going to implement that every time for every element in num layers. We're going to implement this for through a list comprehension. Okay, and we have a question in the chat. Is it too late to ask what heads/multi-head are? I missed the first session. I'm sorry to hear that you missed it, but don't worry, because there's always plenty of time to help someone understand a little bit better what's going on here. So I'm going to actually bring in self-attention a little bit here by talking about the self-attention mechanism in more detail, okay? So I'll go ahead and say that there are 3 main features for the self-attention head. Let's actually put them here. Let's see here. I'll make a little new cell for this. I'm just going to copy and paste this from our previous efforts the other day, or the other session rather. And so they're called Q, K, and V. Now these are tensors of shape, batch size, sequence length, and D underscore K, which is the size of the keys pairs. And what we're going to do is first say that we want to compute the dot products between the queries and the keys. Why? Why is that? It's because we want to get their scores, meaning their similarity scores. How similar are they will be directly related to those dot products. And then when we're done with that, we'll probably have actual numbers as our output. So we want to apply the softmax function, which will allow us to get the attention weights from these scores. And so the goal there being that we actually want to pass them into our transformer model. So we need them to be in probabilities, not in just random scores. And then finally, we did multiply the attention weights by the values. So we take those attention weights that we uncovered, and we know we have some values, meaning a prompt, for example, that the user creates, and we multiply by these attention weights in order to predict the next word. And so then we get an output, and I'll show you what this looks like here. So we're going to use in here something called self-attention. And so that's in the block itself, where we are defining the attributes and just kind of showing how this model is going to work and how it's going to look by giving that a go. Okay. And so then we continued on. We did the feed forward mechanism. And I think we're ready to continue on with our transformer model, but I'll pause for just a brief minute to see if anyone has another question. But that was a really good question, and thank you for that. Yeah, I love it to hear from the audience, to hear from all of you, and learn about what you're interested in, or what you might be struggling with too. And I should say multi-head is just running multiple of these self-attention mechanisms in parallel so that they can all sort of, they can all be used to their full potential with a large data set. All right. So let's go ahead and move along. I'm just going to try and get a little bit further here. Let's see. All right, sorry everybody, I just got lost a little bit in what I was doing. Oh, that's right, we were doing the toy data set. We were doing create a toy data set. So we're going to keep creating our toy data set, and I'm going to show you a little bit about how to do that. So first, we're going to want to import Torch, and we're also going to want to import from torch.utils.data. I want to import data set and data loader. Okay, tensor data set and data loader. Now, where is the tensor here? I got to put that. But these are going to be used when we go to build our toy data set, because we're going to have them in there. So I want to first define some hyperparameters. And we're going to do that for our toy data set. Okay. And so First parameter, I want to look at vocabulary size. That's always a really good one, always a banger. And the next one I'll show you is the maximum sequence length. So we'll use max seq length for that. And I think we said that we were getting increasingly poor responses from this. And so we're going to use 20 as our maximum sequence length. And then the number of samples we'll use as 200. Okay, and so we'll create random sequences to simulate tokenized data. All right, and so I'm going to put some toy inputs, which will just be random numbers, and I'll paste that in here. Random integers specifically. And the shape is going to be as follows. So there's 3 dimensions. And the first is a 0 dimension, so just dimensionless, but it's still important to have this for certain applications, such as doing mathematical operations on tensors. But the second dimension is the vocabulary size, which in this case is 1,000 words. So we're saying that there's 1,000 words in this data set in order for you to learn from. And then we have the number of samples, which is about 200. So that's quite a bit. And then max sequence length is 20. Okay, so this is just, like I said, it's just a toy for us to play with. So first, let's create our targets. Because of course we already have our inputs. For each sequence, our targets are the next word. So for example, you might have some target I equal to the input, and the input would be I guess it would be I minus 1, right? Let's double check. I plus 1, excuse me. Because we're trying to predict the next one in the row. So we can actually write that out. I'll put that in here. All right, and then we'll create a data loader as well, because our computer runs faster if we put the data into batches. So I auto-filled some code here because I think it's right. I'll double check it, but it'll use some tensor data set called, well, actually, I guess we didn't call it yet, but we could call Iris or something like that, which would be a large data set. And yeah, let's go ahead and continue with this. And we'll continue by putting in the next slide. So we're going to actually define the loss function and the optimizer. Okay, so for our language model, we need to have some kind of loss function in order to optimize. And the loss function we're going to use is called cross entropy. Okay, and so has anybody here heard of cross entropy? Do you know what entropy is? So let me give you an example. An example could be when you're cleaning your room. Okay, so right now, if your room is messy, which if you're like me, it's very messy, the entropy is quite high. But as you go around your room and you clean, the entropy goes down. And it's because entropy is essentially measuring the amount of order in a system. So we're going to use entropy to measure the possible number of states that a system can be in. And if it can be in many different states, so in other words, there's many ways for my room to be messy, but there's only one way for my room to be clean, or there's just a few ways that my room could be clean. So those states are quite low in their entropy. And we can use the loss function and the optimizer to get at this, okay? And so we're going to do that next. And I'm gonna pull up the code so we can do that. But yeah, one more thing I wanna talk about before we do that is I wanna actually show you a diagram of cross entropy, because I think it is really good to know about. Okay, I even calculated the cross entropy once, just by hand in one of my streams. But I want to see if I can find you all a really good example of what cross entropy is. Yeah, here's a good example. This equation here. So the sum is over all of the possible states. And in this case, it would be the probability of correct or incorrect classification. And so, you know, if we have a lot of different probabilities, you know, the greater the uncertainty we'll have. So that's going to give us a high value of entropy because we'll have a lot of different possible states. But if the sum is over a small number of states and most of them go to zero, then that is a value with less uncertainty. So that's why we try to minimize this function. And it's great for computing discrete probabilities. And yeah, that's really great. So a couple of comments here that I want to address. We have, why choose 16 for the batch size? That's a great question. So typically we choose something like that, some multiple of 2. First of all, it's really convenient to make computational calculations in order of 2. Think about this. Your computer, how much RAM does it have? It might have 8 gigabytes of RAM when you bought it, or it might have 16 or 4, but it probably has some multiple of 4. So a lot of things in computers are done in these powers of 2. And so if we use a batch size like that, it's just generally easier to think about in terms of computation. And then Sandra Tai said a really good analogy. So exactly, this is cross entropy loss, and essentially possible number of states that contribute to entropy. There's many ways your room can be messy, but there's only one way to keep it clean. So that's basically what the cross entropy is a calculation of. And so when we think about the machine learning model, there's many ways the machine learning model can get the answer wrong, right? It can do the calculations and get the answer wrong like thousands of different ways. But there's only one way that it can do perfect job at getting the right answer, right? And it basically has to ace the test, has to get everything right. And there's only one way to do it. So that's how cross entropy works. And Safiro says, I've recently found this channel and it sounds interesting. So I'm glad you found the channel. Welcome in. We're a very friendly bunch, I think. I guess I couldn't exactly say for myself, advocate for myself in that way, but I think I'm pretty friendly. And certainly the people in the community are great. So yeah, welcome. And anyway, then let's continue along with this part of it. So we're going to do this loss function and optimizer part. All right, and we're going to actually set that up ourselves. So let's see if we can get that going. Okay, sorry about this. Just gonna get the optimization stuff ready to go. So remember, we created a transformer model already. So I'm going to import torch.nn as nn, and I'm also going to import something new that we haven't seen yet. And this is called optim. And we'll import that as optim. And so this particular library here, oh, I forgot to run this cell. That could give me a problem earlier. Always try to run your cells, everybody. Otherwise, they'll run you. Run you around, that is. Okay, I guess I messed this up. Did I finish this? Oh, I guess I didn't finish this. I think there's one piece that's missing here, which is the last piece. I thought I finished that. I don't know why, but yeah, I guess it didn't quite get finished. And so that means we didn't do the forward either. So I'm just gonna put some of that stuff in here now. Oh, sorry. Just replace this with the proper transformer model. Let's run this cell and make sure it works. Oh, this is transformer model. Not sure what caused that problem. But yeah, sometimes you'll just get an error out of nowhere, seemingly, and you have to work to resolve it. All right, and for those of you who are unsure what we're working on right now, I'll send the link so that you can see for yourself. You can download it yourself. But yeah, we're just working on getting through these transformers and learning about them. Okay, it seems like this whole thing needs to just be run. My whole data set is, or my whole thing here is messed up. How did that happen? I got disconnected from my kernel, that's why. Yeah, sometimes it happens. You get disconnected from your kernel. What can you do? You can't do much. All right, so we'll just wait for everything to run. Give it a little bit of a break for you all. Yeah, if you weren't here before, we did a lot of stuff tokenizing and learning about how these models, they think in the form of a token. They don't actually think in the form of text like you and I do. They're going to convert everything that's text into little numbers. Okay, so we're just going to keep working on that. I'm actually going to pause for a moment and just let this run. You can see what I'm looking at right now. Yeah, we did some of this generator stuff. This was really fun. If you weren't able to come for this, come to like cell 18 or cell like 17. And we actually loaded up ChatGPT-2. Funny enough, GPT-2 is small enough that you can run it on your own computer. So that's what we did earlier, and that's what's coming and spinning up right now. Pretty cool, right? And check this out. We actually said like once upon a time in a distant galaxy. That was our prompt. and it completed the phrase for us. So that was really cool. And then I guess we did this too, but it's, yeah, I'll just keep going with this. We're almost through everything actually, which is good. Means that we didn't have too many errors, but I think our kernel just timed out somehow. Sometimes that happens in Google Colab, but it's a good way to review anyway. So we have our tokens and our tokenizer, our tokenized function. And I guess this was the part here that we kind of had some issues with when we started to run into. So I'm gonna just rewrite all this stuff so that it's properly done. So first I'll just write this slide here. And this is where we did the self-attention stuff. So remember, we had linear layers for queries, keys, and values. And then attention is when we apply this softmax function. We do a matrix multiplication of our queries and our keys to find out the semantic meaning of each word. And we compute the attentions in that way. And then we multiply them by their values to determine the final output. And then we would concatenate everything and pass through a linear layer at the end to return everything back into its original form. So that's what this feed forward is doing in the forward method in this self-attention head is doing. And then we went on and we said, okay, why don't we go on and do a feed forward method as well, which is another part of the transformer model. And so feed forward involves us using an activation function. So ReLU was the activation function that we chose, and it just introduces some non-linearity in that. Okay, and so yeah, then we just had another forward model, which was which is applying all of these things, and we tested it out. Typically, these feed forward modules, they have more higher order embedding dimension than the embedding dimension. So the feed forward module might have 512 layers, and this is what we call a hidden dimension, where the original embedding dimension was only 128. Okay, so we're just adding a little bit of noise into there. We're adding a little bit of nonlinearity, and yeah, it's kind of cool. Okay, so Zafiro has a couple more questions. I got your message here, Zaltova Tree, if you have this right after Googling, but I didn't get any other messages. So just to letting you know about that. And then Zafir says, MLH is mainly focused on building rather than breaking into things. I'm mainly focused on red teaming. So if you're interested in red teaming and cybersecurity, there are actually a few opportunities that you could take advantage of. There's this thing called the fellowship, which I just sent a link to. And we sometimes do have cybersecurity tracks in our fellowship program. So if you are interested in cybersecurity, oh, sorry, everybody, that was pretty loud. That would be something to check out. And another thing you said is that you're getting a feel for whether these programs fit your goals. So definitely check out that fellowship. But yeah, no problem. Happy to help and point you in the direction. Hopefully it's the right direction. I don't know, but we never do know until we try it out. So, okay, now we're gonna, I'll go back to our block, our transformer block. That was the next thing we did. And the transformer block is where we're putting together some of these ideas. So we know that with a transformer block itself, first we take the information, we pass it through an attention head to get those attention scores. And then we normalize the layer using a simple layer norm, which is just making the weights on the same scale as everything else in the transformer model. And that helps with these mathematical operations so that nothing gets too far out of the normal range, I guess, and makes the model either explode or just flatline, basically. And then here we did .ff, which was feed forward. So the feed forward method that we built, and then another layer normalization, and then finally dropout. And we explained it, we learned that dropout is basically when you just try to remove some of those nodes in the neural net, so that you can make sure that that those connections are not just overfitted, and that they're real connections. Just like out of sample testing, if you ever heard of out of sample testing or OOS, that is a good way to think about it. And then there's always some sort of forward method in these blocks, because neural networks are made of many different layers that connect to each other and sort of interact with each other. So with that in mind, this is really how it works. And we have feed forward with residual connection. So residual connection means that you not only do you take the apply attention to your input, but you also add a dropout from something else and normalize. So you're kind of mixing it up, adding a little bit of a residual connection, as we said. And then here you're just doing feed forward in the same exact way. So residual connection is a key part of the transformer block. And when we implement this, you can see that the way that this works is very similar to, so if we print out, let's just print this. We print out D model dimension is 128. So the transformer block has that as its last dimension. And then we had a number of heads as 8. And you can see that if we go all the way back to where we started doing this, our input that we fed in was 2 and 10. So we're getting that as our output as well here after we pass through the transformer, right? So then after we did transformer block, this is where we're moving on to what we're doing right now, which was the transformer model portion. So that was here too. And remember, in the transformer model, okay, we have some additional things we're doing. So we're doing the embedding, where we first get these vocabularies and relate them to each other. And then we're getting the positional embeddings. So we talked about that and how that's telling the transformer where the different words in the sentence are located. And then we create a stack of transformer blocks. And again, we get this error, which I think is really funny because, oh, did I just delete the transformer block? I think I did. I confused myself on this. Okay. Yeah, you can see how it can get a little bit hairy after a while working with this same notebook. I might try to break up the notebooks into little smaller ones later. But yeah, so now we can see our output here. And we'll just go through it. So we created a stack of many transformer blocks, as many as we want. We can just set the number of layers to however much we want, and it should actually improve over time. Zelkovatry asks, what would happen without residual connections? So that's a great question. And in order to understand that, we would have to think about, what is the value add of machine learning? So with machine learning compared to like linear regression, for example, it's different in the sense that you can account for nonlinearities and things that are not really well understood, how they relate to one another. And so that's really important. And so when we do the activation functions, we're adding in nonlinearity. And when we do residual connections, we allow the input of one layer to be added directly to the output of that layer, the layer before the next one. And so it's going to help us bypass those nonlinear activation functions and prevents those nonlinear activation functions from exploding in either direction. Okay. So yeah, it's just a good way to maintain the model stability and make sure that the model actually converges. Because we want to take advantage of all these great nonlinear relationships that we can find with the neural network. But if we just leave it to this ReLU activation function, and you can see it here. Where was it? Oh. There it is. If we just leave it to this ReLU activation function and just feed forward every time, things could get kind of hairy because of those nonlinearities. So that's why we use residual connection. Yeah. So anyway, very good question. And let's continue along. Oh, would they get forgotten? Exactly. So what would happen is they would get forgotten. And yeah, you could just end up exploding in one direction, your model, because, if you think about these nonlinear activation functions, a small difference in the values can create a really large effect. And so you could get a runaway output where it just gets larger and larger and larger in one direction, and it makes a really strong prediction, which is not actually, it's not easy to optimize. So yeah, you don't want that to happen. You want to keep the model stable and highly normalized and not see these really large values that can explode the model. Yeah, because right, like if there's even a small little change in the number, in some of these nonlinear cases, that could mean a really big thing. But in reality, it's not there. It's just part of the activation function. So yeah, that's how we keep it sort of grounded, connected to its past life before it got pushed in some random nonlinear direction. So anyway, good questions though, really good questions. Okay, so let's continue on then. And I think, well, let's see. Yeah, so we have the layers of transformer block, final linear layer to convert to vocabulary logits. And then the forward method here is basically going to just apply these token embeddings, add the positional embeddings, pass through all the transformers, and then generate the logits. So yeah, if we were to actually have some model outputs here, you can see that we expect 4 because we have 4 batch size. And remember, there was that question, why is 16? Well, why 4, right? It's just very common to use these powers of 2 in programming. And our dumbing tokens, so we just generate just some random tokens from our vocabulary, and we'll just make them, we'll just make some examples. These are just like you could think of as different sentences. And so, yeah, then we just have our model and we passed our dummy tokens into it and we got our logits, which are our generated logits. And if we go ahead now and we want to define the loss function in the optimizer, we're going to rely on all of this stuff. So we're going to define our model from this transformer implementation, and we'll just use this model that we just built. Let's actually, let's actually build a new model just so that it's on the same thing. I'm just thinking ahead, because if I end up separating out these these different ones, I'll want that. I'm not going to want to have to figure out which cells rely on which ones. So we'll just give it some different stuff here. The number of heads we'll give as 8 heads. Feed forward, this is, remember, the hidden dimension. And let's just do 2 layers. So that means that the number of transformer blocks is going to be 2. And we'll just set the max sequence length. What did we set it to before? 50? All right, let's use 50. That seems pretty reasonable. All right, so we're cooking. And now we're going to set the model to training mode. So we're going to do model.train. And you might wonder, wait a minute, we didn't define any train. Well, this is pre-built into Torch, into PyTorch. So we don't have to have some training mode. It's already there for our model. So, all right, and now we're going to define the optimizer. And you might be wondering, what is an optimizer? Well, the optimizer is going to basically solve the gradient descent problem. And so, yeah, basically this is how we're going to iteratively solve our machine learning algorithm and get to minimize that cross entropy loss. So optimizer, we'll call it Adam. That's a really common optimizer. Almost everybody uses this optimizer for gradient descent because it's very efficient. And I typed this LR parameter too. I didn't know if you noticed that, but it's called the learning rate. So Adam wants to know a learning rate that will tell it how fast should I converge on a solution. You know, it might try out different angles and try to make a really good solution. But if it doesn't have that much time to converge on a solution, it might just see something good nearby and converge over there. So the higher the learning rate you make, generally speaking, the faster it will converge. It will have a lower, quote unquote, model temperature, you could say. The lower the learning rate you make, the more free the model is to, quote unquote, experiment in different directions and really try to minimize that loss in the long term. And so that's what they call high temperature. And you can get some wacky solutions by using a low learning rate, but 0.001 is a pretty standard one, pretty middle of the road. So let's now do the loss function, which, remember, this is where the cross entropy goes. We were talking about making our room and saying that there's only one way to really make your room clean. So we're going to look for that one way. And the way we're going to do it is by having some criterion here. So we're going to use cross entropy. Oh, I just typed my last name accidentally. Okay, cross entropy loss. All right, and so that's the right one there. Okay, and so yeah, we now have that done. And let's see, what else should we do here? I think we already did our toy data set, but I might have accidentally deleted that. So I'm just going to go through and make sure that I still have a toy data set here. I think we had it after our logits. Yeah, very good. So let's go ahead and train. So yeah, we did our criterion. So we're gonna do 5 epochs of training. Oh, I had a red arrow here. Strange. Okay, I don't know what that came from. Let's do 5 epochs of training. If you're not sure what an epoch is, it means that you know, you might have like 5 different stages of training. And yeah, exactly. Model temperature. That's exactly right. Model temperature. So you might see, you see some of these things on the internet and you think, oh, okay, that sounds really good, or like, um, but they don't really explain it that much. So yeah, it's really cool to go deep dive into these things because you can kind of understand what people are talking about in the space. And yeah, that's what's needed to encode a clean state of room than messy state. Um, yeah, so well, actually, I would say that you probably need the same. Yeah, oh yeah, that's right. Thank you, Azal Coventry. That's exactly right. More bits are needed to encode a clean state of the room than messy states. Yes, absolutely. Because if I give you instructions on how to clean my room, how many pieces of paper do I need for that? I need a lot, probably. Um, but if I give you instructions on how to make the room messy, I can just tell you in 3 words, make it messy, and you will know how to do it. So that's a very good observation there. But let's do 5 epochs of training. So these are just how many times will we take a pass over the data. So we're going to just say number of epochs equals 5. And let's use a loop here. So we're going to use for each epoch in the range between 1 and the number of epochs plus 1. So that'll give us 1 indexed variable. So just epoch 1, epoch 2, epoch 3, so on. We're going to start with some total loss. And this is like the cumulative loss parameter. And we want this to kind of converge so that we're not taking huge loss hits every time we go over the data again. Once we stop taking massive losses, it means that we've pretty much gotten to the lowest loss possible. So that's why we keep track of this parameter. And then we're going to take for each batch input, and batch target in loader. So remember, we have this toy data set, which is just a bunch of random. Look, this is literally random words. So our training data is just completely random words. It's not like Wikipedia or anything. So we're probably going to get a model that just makes random words, but here we go. So, that's reason I bring that up is because that's what we're loading in right now. We're loading in these inputs and targets. So these, the sequence and then the last word omitted, and then the sequence with the starting at the second word. And then we do optimizer dot zero rad. And so this is clearing the gradients from the last step. So it just leaves the optimizer with a blank slate. And so we're going to find the logits from this particular input. So we apply the model to this batch that we have, right? So the loader has many different batches. I think we said 4 or something like that, or 16. That's right. So we have 16 different batches. Each time we're going to do some predictions. And we're going to, after that, we're going to optimize them. So we're going to reshape, because the optimizer works in this way. So we do logits.view, and we're going to view them, and we're going to use -1 and vocab size. So it's going to basically transform the batch into these single file, I guess, strings. So just long strings of data. And then we'll also do the same thing with targets. So we'll do logits flat, targets flat. And we'll do batch targets dot view -1. And we're going to compute the loss now. So compute the loss. And we have to do that by using the following. So we're going to do loss equals criterion, logits flat, targets flat. And then we're going to add that loss to loss.item. Okay. or add that to the total loss. All right. Oh, I forgot a step here actually. We're going to do loss dot backward, which back propagates the errors. And yeah, so you're going to back propagate the errors with that. And then I'll show the average loss at the end. So I'm going to copy these from my other thing here. Yeah, so we're going to just print this out at every epoch. So we'll know that things are going well if the average loss is going down over time. And so let's just run this. I'm not sure if my computer is powerful. Oh, it's definitely powerful enough. Okay. So, oh, interesting. We might have messed up somewhere because we got the same loss every time. That's a little weird. Must have done something wrong. Let's see. Okay, let's see. Oh, forgot to step the optimizer. Okay. So in this case, if you look at what we do, we back propagate the errors. Does anybody know what that means? Maybe you don't know what that is. It means you compute the gradients for all the parameters in the model that require a gradient. So you're just going to actually trigger the back propagation algorithm that calculates the gradients to find the optimal solution. But then we have to actually step the optimizer. So what that means is that we're going to update the model to tell it like what direction to go. So you can think of the loss dot backward. This is telling, so loss dot equals criterion. This is telling us what is the current loss. Loss dot backward is saying, all right, this is where you need to go, right? Like to get a better answer. And then optimizer step is what tells the model to update. So now our model actually updates and the loss actually goes down. So we're learning about this random thing that we made. Okay, so now we're going to do another thing, which is going to be, we're going to evaluate the perplexity of the model. So let me show you. Let's just share these, what we did. I'll summarize that before we go to perplexity. We iterated over the epochs, processed each batch from the data loader, calculated the model outputs or logits, and then we reshaped them appropriately. And that means flattening them. And then we calculated the loss, backpropagated the errors, and we updated the model parameters using optimizer.step. We almost didn't do that. That would have been pretty bad, but now we're good. And then we print the loss to monitor progress. Okay. Yeah. So now we're going to be on to evaluating the model. And I'm going to tell you about an evaluation criteria called perplexity. And so evaluation helps us understand how well our model is performing on unseen data. So one of the common metrics for a language model is perplexity. And maybe you've heard of the company Perplexity. I think this is where their name comes from. I'm not sure, but they are probably inspired by this metric. So yeah, basically it's how surprised the model is by the test data. So lower perplexity means that you're not as perplexed, essentially, and your model is better. So let's try to do that. Let's try to actually get that going. And then a question here, can you explain the differences between a hidden Markov model and a transformer model? I am not so familiar with a hidden Markov model, but that's a good question for the chat. Maybe someone in the community knows. But yeah, so anyway, I wanted to talk to you about perplexity, and let's get that going. We're going to get a little calculation of this. So we're going to import some features. We're going to import math, import torch, import torch.nn as nn, which is the neural network modules. And I'm going to define some function called evaluate perplexity. And we'll put in a few things. So we'll put in model, data loader, criterion, and vocab size. And those are the 4 parameters we want to use. It's the transformer model itself that we'll pass in, and that data loader, which is going to be the data loader for evaluation data set, not train, but this time we'll use evaluation. So it's very important to use different data when you evaluate compared to training, because you don't want to evaluate on the same thing you're training on. You're not going to get the right answer. And then finally, a criterion, which is in this case a loss function. So we'll tell it to use cross entropy loss here. And then finally, vocab size, which is the size of the vocabulary, which we've just been dealing with that same 10,000. So, all right, now let's return the perplexity, which is the exponentiated average loss. And so first, I want to set the model to eval mode. Okay, and that will take it out of train mode. And we want to do total loss equals 0, just like we did before. And total tokens, we'll use 0. And so I want to start by saying, as long as torch is on, we're going to sort through different batch inputs and batch targets in the data loader, just like we did in the previous time. And so the logits are the first step. We take the model and we pass in the batch inputs. Okay, and so the model's going to fit to these. And then we're going to do the same thing we did before, where we took logits flat, just like we did before, targets flat, and the loss function, which is that same criterion, logits flat and targets flat, okay? And so we're using that cross entropy loss function in this context. We will do that. And now we're going to multiply the loss by the number of tokens in a batch, okay? So let's do that. We do total loss, loss.item times batch inputs, size 1, all right? Sorry, that's not right. Sometimes when Gemini gets going, it tricks me into thinking it's right, but it's not. So we're going to use targets flat size 0. All right, because we want to multiply by the number of tokens in a batch. All right, and so now we're going to do the total tokens. And that's just targets flat size 0, just like we saw before. And so now we can actually calculate the average loss. And we'll say that's the total loss divided by the total tokens. And the perplexity is the e to the of the average loss. So we are now able to compute and really understand the perplexity. So why don't we try to evaluate this now? So we can just type evaluate perplexity and we'll use our data. So we'll use model, loader, I think it's called loader. Let's see. Loader, yep, loader. Criterion, I think we already defined that too. Probably way up there we did that. Or maybe we never did that. I guess we'll find out in a minute. And vocab size. All right, we did. So we get a perplexity. And our perplexity is 21. So it's a pretty low perplexity. That's good. And we now know that our model is pretty accurate according to this perplexity measurement. And so now I want to move us on into the next part of this, which is, yeah, so we did this part, but I want to put us into actual inference, okay? So we're going to use this trained model in order to generate text. And I don't know if you've ever seen this, but sometimes you'll see on TV, on like the news or on some academic article, they'll say, oh, we've started to generate poems as if they are in the style of Shakespeare, for example. And so what they'll do is they'll do this inference where they'll just generate some text and say, let's train on Shakespeare and generate on it. So since we trained on random gobbledygook, our model will also be random gobbledygook. And so that's what we're aiming for in the end. So let's see if we can do it. All right, so we'll define generate text, and we'll put a few different things into it. We'll put the model, of course. We'll put our initial sequence. So this is what we feed it at the beginning, which is probably like the first one in the data set or something like that. And then we'll do some max length. So max length is going to tell it how big am I allowed to make my, my response. And then vocab size, 1,000, 10,000 actually we'll do. Okay. And so we'll start by putting the model into model.eval mode. And we will make a sequence. So we'll just pretend that this first sequence is our generated sequence. Okay, by cloning that. Oh, sorry, not doing this yet. Sharing here. That's right. Buy some gobbledygook. Actually, buy some gobbledygook coins. That's next on the next stream. I'm going to sell gobbledygook coins to all of you. Okay. All right. Just kidding. But yeah. Okay. So let's go ahead and continue along with our generated sequence. So we're going to generate some tokens until we reach the maximum length. Now, that doesn't necessarily mean it's going to be always that long, but we'll just generate those tokens, and we might have some empty tokens at the end. But we're just going to make a for loop that we don't necessarily need a variable, but it's just going to go through everything in this max length, right? So we're gonna start with our initial sequence, which will only go up so far, and we'll just continue along until we hit that max length. And we'll just say, hey, give us some logits here. Give us some some words, basically. And so next token, logits. We're just going to take what the logits we got. We're just going to say, give us that last thing, that last token in the sequence. And we're going to use greedy decoding. So here's what greedy decoding is. You might have wondered, when you saw that word, it's a strategy to generate that next token. And yeah, so we're going to feed the sequence into our model, pick the next token, append it, then feed the new sequence into our model, pick the next token, and append it. I don't know why they call it greedy. I guess they just call it because we're always asking for a new word, I guess. But that's kind of greedy. I don't know why, but it is. So, all right. So let's just go next token, and we're gonna use torch, argmax, and we're just gonna take the token with the highest logit. So in other words, just the token that has the highest probability of appearing. And we'll just keep that. And so then we'll have finally some generated sequence. And that will just be the concatenation of all this. So like I said, we're just going to concatenate everything. And that would be our generated sequence. So let's create an initial dummy sequence. So we'll just have some initial dummy sequence here that will pass through, and it'll literally just be random integers, so random tokens that will pass in to our transformer. And let's print that just to look at it. So we're looking at just something totally random. Oh, I wonder what the problem is with that. Oh, there it is. Wrong. All right, so here's our 5 different tokens. And if we type generated sequence now, we're just going to simply apply our generate text model. Oops, sorry. Remember, our generate text model requires at least model an initial sequence, and we don't need to define these other two. Or let's just define them, actually. You know, let's just keep them this way. I don't really care too much. All right, so here's our generated sequence. So we just made like a new sequence based off of the old one. Sometimes it'll be the same as before. You can see that. Sometimes it'll be different than before. But we always add on some amount. And so let's generate a dummy token sequence and a random sequence of IDs. And if we have a tokenizer, we can actually look at what these things say, right? So let's actually look at the tokenizer and check this out. So we'll import tokenizer. And we'll say tokenizer is, we'll use this auto tokenizer from pre-trained, and we'll use this BERT base uncase, which we used this before, I think, in a previous part to this series. But you could use whatever tokenizer you want, I guess. But then we're going to decode what the generated sequence said. So we're gonna use this tokenizer.decode. So we'll use generated text, we'll call it, and we're going to use tokenizer decode. I don't know if we need to do all this stuff. I think we can just leave it like this, and we'll just generate the text. And so we got some totally random nonsense. Wow. Okay. Yeah. Interesting. Racing quickly himself, predecessor Daniel. I feel like you could tell this to somebody and they might form some kind of, new following of this LLM model. Yeah. But there you have it, everyone. We just created our first transformer model. And I actually think that next we'll probably create a more, more like legitimate model, I guess I could say. Something that's not going to just randomly spit out tokens. And it'll actually, tell us a little bit. But yeah, it sounds like a Muppet. Yeah, absolute hype for word salad. Yeah, no, it's cool. It's really cool because it's generating these this word salad, but it's doing so using our transformer, and we don't need to pass in random words. We could pass in Wikipedia text, for example. That would be pretty cool. And so maybe we'll do that for next time. But yeah, I wanted to just see if you all have any questions before we continue. All right, so why don't we take a quick break, just about 5 minutes, and then I'm going to start on prepping us for our next step, which is going to actually be to implement this on Wikitext, which is the original algorithm that we wanted to implement it on. Now, we may not actually get to that, today. We might have to wait for the next part, which is only in a few hours. We'll be doing the next part. Um, but we can at least get started on it and get ourselves going a little bit here. So yeah, let's just try to go after that a little bit. So just give a brief break for that. All right, everybody. So we had a couple of minutes to chat about to take a break. Sorry, I just needed to grab a little bit more water because you don't know how you definitely need some water when you're doing a lot of talking. But I'll tell you about the next part actually. So the next part of this is going to be at 3 p.m. Eastern time. And I'll send you a link so you can add it to your calendar. And so part 3 is 3 p.m. Eastern time tomorrow. Right, so there's the event. Yeah, it'd be great to see you there, and we're gonna go through the rest of this, and then we're definitely gonna finish our transformers. I mean, we'll be done with our transformers, but we'll move on to RNNs after that. And RNN is another model that sometimes gets forgotten because it didn't get as popular as the transformer architecture, but it's still a really useful thing and still very widely used in scientific applications and all kinds of things. So we'll take a look at that and learn about it. And yeah, that'll be great. So I want to just show you the setup for this, how we're going to do the wiki text, and then we'll be done for the day. So we'll start, and I'll show you. We'll just import all of the things that we use for our model. So it's things like load data set. It's things like torch, and then we have our minimal transformer model. So remember, we have to put in all of these functions that we had before. So things like our self-attention block, our self-attention function, our feed-forward function, our transformer block, which remember is a mashup of those, but we normalize and we drop out to keep things running smoothly. And our transformer model, which is basically just a bunch of different transformer blocks, but we put embedding layer and position embedding at the front. And so there we go with that. And we're going to load a different data set, which is going to be, it's going to be called Wikitext. So I think you may remember that we used Wikitext before. You may not, but I'm going to add a little piece of text here so I remind myself. So for part 3, this is all, we're doing some work for part 3, so we don't have to do it tomorrow. But we'll still do a review tomorrow of this because it's important. But yeah, we'll just keep that for part 3 for now. And so we load the data set as well. So the data set here is going to be Wikitext. We're also probably going to use a more powerful computer tomorrow because although we can use our CPU, we probably don't want to be honest with you. It's going to be really tough to do this with our CPU. So we'll probably just hold off on that and use a GPU. I have a bunch on my computer. I can change to a different runtime, which has A100 GPU, which has like 100 gigabytes of RAM. And yeah, it's just definitely going to be faster than this simple CPU that we have, where we essentially have just a very normal computer we're looking at. But yeah, so we have a number of training samples here. And then, yeah, I mean, that's pretty much it. And I'm just going to leave this up for next time, and so we don't get too far ahead of those who join us on part 3. But yeah, thank you so much for coming, and it was great to meet some of the new folks who came, and glad you found us. And it's also great to see some of our veterans of the community, because you all are there making things great and helping out everybody. So next up, we have a stream from Charble about Intro to ROS. So it's called Intro to ROS, Charble, and the stream starts at 8 p.m. Eastern time, or 11 p.m. Eastern time, I think. Yeah, 11 p.m. Eastern time. And here's the link to check in. Yes, I think, well, actually, yeah, I think it's robot operating system, but I'm not sure, okay? So don't quote me on that, but I think, yeah, actually, I don't know what it is. But you know, Cecilia was telling me that it's really cool. So I think it should be very cool. But all right, so take care, everybody. Thank you for joining, and hope you have a great rest of your Global Hack Week. See you next time, I hope. Bye-bye.